So we continue and then try to finish this class. Okay, we back to here. So I will explain. Okay, so for the downsampling for the CSP darknet and in the detail. So they have a CBM, CSP. So from up to here. So from stage 1 to stage 5, the combination, basically the combination of the consists of a CBM and the CSP. Okay, and the CBM is a convolutional batch normalization, and they use mesh instead of ReLU. So we next page 13 here. Okay, so my student explained this one in detail here. Okay, but I explain. So we are convolution to extract, right? What's the purpose for batch normalization? Is this one. They try to normalize. Usually based on the entire batch, we normalize to the mean, normalize to the standard deviation. So we try to solve the gradient vanish problems. Because when you do the gradient, okay, and the probability will become lower and smaller, and become zero, and become so vanish. So try to solve these problems. We do the batch normalization. Try to normalize back to the zero between 0 and 1. So it's batch normalization. Sorry, batch normalization and try to solve gradient vanish problems. Okay. And this one, usually we use this one, ReLU. Okay. And ReLU easy is because there's a linear here. And after the zeroing, the negative part is just 0. But I think this is what I think, because you do a lot of gradient, right? So this is not good. This is not continue because it's not it's not smooth. This one not smooth. So it's not smooth when it's not good for the gradient process. So we want to be more smooth here. 因为那个要连续微分嘛，微分是像 BBB 嘛 ，gradient descent BBB， 那微分是越 smooth 微分的话还会 continue 嘛。那这个有这种转折的地方，微分就会出状况，没办法，就是会出状况。So because to solve this gradient problems, so they use continue here. Also, they try to mesh, right? So be more smooth. And also they try to keep the small negative value instead of zeroing. Okay, so that's why they use mesh. So for the, sorry, back to the page 12. So for the convolution here, okay, in the CBM they prefer use mesh instead of ReLU. Okay, next one is a CSP. So what's a CSP? CSP here. So CSP include this one, include 2 paths. And CSP here. Okay, so this is what's the CSP is cross stage partial connection. That's meaning for each one here, suppose is a 64 maps. Suppose this 64 input is 64 maps. If a 32 go through this path, the other 32 go through this path. So each map is divided by 2. Half maps go this way, the other half map go this way. The purpose is try to reduce the total number of parameters. So 32 have this one, this extraction, and the other 32 has more extraction information. Extraction doesn't mean good or not good. Extraction meaning you have more convolution. More convolution is you extract more information. However, your output of convolution will lose more more raw data, more than original information. Okay, so deeper is good, but in the other way, it's more deep. You extract more information, but if the input data, your texture is less, not so many textures. Okay, so more deeper is sometimes not good. But here, this one, don't confuse with this one. Difference. Okay, this is shortcut, the residue, and this is separate map to two parts. So one part is more deep, have a extract more information, and this path doesn't extract such more information here. Okay, so what's the CBL? This one. So CBL only different compared with CBM is that the upper here is and the renew, they use liquid renew. They use liquid renew here. Okay, so liquid renew, back to page. Sorry, page 13. Okay, so CBL, they use liquid renew. Okay, so liquid renew just try to keep the same, keep a negative input. So mesh and liquid renew, they want to keep the negative value instead of a renew. So the same. Okay. Then second one is liquid renew. Yeah, this one, liquid renew. He said they can solve the gradient range problems. But actually, I don't really know this one. I said no, mesh is more smooth. More smooth is good for gradient descent. Okay. For the liquid renew, why they can solve the gradient range problem. I don't know this kind of a saying, this kind of explanation. I'm not sure. Okay, but it's better is that they keep the negative value. That's important. Yeah. But here you will see from CBN and CBL, when you see the output here, this downsampling, this upsampling. You'll find the upsampling as no CBN. They only have a CBL. Why? Downsampling has a CBN because they have a mesh. It's continuing. The upsampling, they don't have a mesh. They use liquid renew instead. Why? Okay, I use my way to explain because probably I'm wrong. I just use my method, my way to explain it. Because it's downsampling and they have a more deep, more convolution. This more deep, more convolution. So they need to have a continue. For the upsampling, they just want to keep more information and quickly upsampling. Okay, so whether it's a continue or not important. Faster is important, and easy is important. Okay, so this just use this liquid renew. Okay, so they have a, if this bigger than 0, they use one linear. So this is a linear. If it's less than 0, negative, they use the other linear. So let's use 2. And linear is easy, just map it. So it's easy to process. Okay, so both method compared with renew is because renew has no, after the negative, there's no value. They say they feel it's not good because the zeroing. They want to keep more information here. So that's why they use mesh. They use liquid renew instead of renew. Okay, and the other is one is a continue, smooth. The other is not so it's not continue because this is about a gradient descent, and this one is easy to do the linear mapping. Okay, so this is my explain. And what's the CSPX? CSPX is the input here, right? So if you have 30, suppose 46 maps, 32 maps come here. The other 32 maps come here because they want to use, actually they have a little bit wider, okay? Because 2 paths, right? A little bit wider. But they, one path, they don't have a they don't want it so deep. The other is more deep. Okay, so here for the rest unit, rate 1. What is this one? This continue to dip. Sorry, convolution, sorry, CBL, and then this shortcut. So this is the residue. We have shortcut here, and just add together. Okay, so there's a shortcut here. So that's meaning for the rest unit CSP, we bet to here. See, CSP here for each stage, CSP 2, 3, 4, 5. So each stage they have one CSP for the downsampling. Here they don't have upsample, they don't need to use CSP. Why? Because it's a backbone. Backbone they want because they feel resonate is good. So they improve resonate, but they get the resonate idea. So that's we call rest, this one, rate 1. And rate 1 is a rest unit. Okay, so rest unit, the best idea is resonate. They have a shortcut here, and they have a deep convolution here. Okay, and finally got the result added together. Okay, so both are different. This CSP is divided by map to 2 parts. Inside CSP, they have a shortcut here. Okay, but this is for the backbone only. For the upsampling, there's no more CSP. So, Zhang Hanzhou and Professor Liao, they concentrate on this one, and this is PNet. Okay, so page 13. Okay, so we already finished this one, and the last one is SPP, spatial pyramid, spatial pyramid pooling. Okay, and SPP is more wider, and they use different maxima pooling, like a 1 by 1, 2 by 2, 3 by 3, or 4 by 4, and we will explain this one very soon. Okay. So here, after we do PNet and the output, and here is head. Header, we try to do the bounding box. So the YOLO V4, the header is the same as YOLO V3, exactly the same. Okay, so the same loss function. And we finish this one, and page 13 we finish, and page 14, okay, this one the same, we finish this one. So for the head, okay, for the head part, this one, okay, so we have 2 scaling, stage 3, stage 2, stage 1. So this one, so this three stage is the same as this 3, 4, 5, and this lower resolution, the higher resolution. Okay. So we have 3 scales. For each scale, we have 3 anchors. So the anchor 1, anchor 2, anchor 3. So total is the same as YOLO V3. 3 by 3, total 9 anchors. Okay, so we have 3 scales. So each scale, we have 3 anchor here. However, the anchor here, before the anchor ratio is fixed, is 1 by 1, 1 to 1, 1 to 2, 2 to 1. So the anchor ratio are fixed before. But here, as I understand, the anchor ratio here, they use k-means. That's meaning, this was they collect all the training data bounding box, okay, and they try to classify to 9 classes. Okay, the 9 classes, 3 different scales, 3 different ratio. Okay, so this is not 1 to 2 or 2 to 1 or 1 to 1. No, it's based on the cluster ratio. Okay, and then here, output here, this loss function is exactly the same as YOLO V3 and YOLO V3, the same loss function. Okay, so total has a 3 by 3, 9 anchors. And for the contribution for YOLO V4, I say, first of all, they do modularization very well. They have a backbone, they have a neck, right? Neck 1, neck 2, that's PNet, and the head. Okay, so this one, they have a backbone, they have a neck. Okay, and if you do one stage, so this is a one stage, this is output. If you do one stage here, one stage here, and you have anchor, one stage is like what we say here, one stage. So you have one stage. You can use two stages for the head. Two stages, the first one stage become region proportional network. So here can be region proportional network, and you have a bounding box. And based on bounding box, okay, this bounding box, you get a feature. And so this bounding box, this feature here, got a feature here. It's got a bounding box, and this got a feature. So you have a bounding box, you have a feature, okay, and try to do the two stages. So one stage we call dense prediction because it's pixelwise for like 7x7 grids. So each grid you need to consider we call dense, middle ground dense. For the region proposal, you only care about the output of region proposal, just based on the region, the output region proposal network, and you do the feature and try to do the refinement or classification. They call sparse prediction, 稀疏的, because it's based on feature plan network. Okay, so the other contribution for the paper of YOLO V4 is that they do good organization here. So they list for input either page or image. For the backbone, they have several methods. They list the several methods. For the neck, they also have the traditional method or PNet for the neck. For the head, that's why I said for the head, they have one stage head, two stage head. So they organize all paper in the YOLO V4 papers. That's a good one. Okay. And then for the activation function, they also list, have a renew, liquid renew, have and the mesh. Okay. That's good. And then for the other important one is for the data augmentation. Here, data augmentation. And we'll talk about this one very soon. Okay, so we skip and okay. Page 20. In page 20, okay, this briefly organized. Okay, actually my student organized. Okay, they have a backbone, right? We talk about a backbone. They use a CSP. Neck, they have a SPP. They have a PNet. For the output head, they use the same as the YOLO V3. Okay. In here, YOLO V4 also talk about two term. 他讲了两个名词哈，一个叫 back of flippies， the other back of specials. Probably it's not easy to understand, but I use my way to explain to you. Okay, so for the for the flippies, actually it's about your data. For the special, it's about your network, the inside network. Like they talk about mesh activation function. They talk about how do you design your topology, your network. So the special is about your topology, your network. Okay, see, this is the same. But this is backbone, this is detector, this is header. And for the free piece, talk about the data. Okay, and talk about your loss function. This loss function is the data. But this one for is topology. We'll keep going. So that's what I try to explain to you. This you read by yourself. It's fine. Okay. So we talk about CSP. That's for the backbone. Okay. And what's the CSP? Is cross stage, right? Important partial. Partial. It's meaning here. So usually our backbone is for the original input, right? Into convolution extract and shortcut to here. And this kind is like a dense. We have a dense net. So it's like a dense. Dense meaning what? Meaning for the next stage, and they connect all the convolution results from the previous stage. So they become dense, middle got dense. So that's meaning, again, they have a convolution, got the result, and they connect to next one, and also copy this one. So they have more information here. And based on this one, they do dense convolution, keep convolution, and result is concatenated with the original one. So they keep doing this one, and finally you'll find out your final output here. Have a lot of information for each stage. That's meaning for the dense is meaning for the output for each stage, they will connect to the final output. For each stage, their output will connect to the final output for each one. This one will connect to here, also connect to the stage 3, stage 4. The same here will connect to next one and connect to the last one. So up to the last stage, you have a lot of connection. So they have a lot of parameters. Okay. So dense block is good, but it's not easy to modify because it's complicated. Not easy to modify if you want to modify. So, go down. Keep going. So they try to improve this one. They want to have a dense information, but dense information is complicated, have many parameters. So how can they improve? So here they do the partial. Partial connection is like the example. If we have a 64 maps, have a half 32 maps, directly shortcut to the output. The other 32 will connect to the dense block. So they will reduce the parameters. Originally is 64 maps. They divided by two parts. One is 32, the other is 32. So only the other half go through the dense block. So they can reduce a lot of parameters. And here they have this path can keep more original information. So for example here, so original image is the same as this one. They have a lot of maps. So they cut it, half of the maps directly shortcut to the output here. And this one, only half of maps use dense. So they come here and convolution and come here. And so this is dense, the same, but just partial dense. Okay, so they reduce half of the parameters. So and then they apply this one to the YOLO V4. Okay, so it can be faster because they don't have a lot of parameters, but they want to be higher result, higher resolution. Have a better result. So they use dense, keep more information here. So finally here we can keep more information. Okay, and this is the detail about the CSP darknet. So the one time sampling, 1, 2, 3, 4, 5, 5 big stages. Okay. And we talk about SPP here, SPP. So what's the SPP? Sorry, this block here. Actually, it's SPP. Okay. Can I move up? So I try to do this one. You cannot move up. Oh, you don't have a mouse. Oh, I need to use this one. Okay, we keep going. So what's the SPP? The purpose for SPP is this one. Your output size will fix no matter what kind of input size. So no matter what's WH in the input size, your output size can be the same. So that's good for what? Good when your final connection is a fully connected connectional, not convolution. Connectional is a neural network. It's fully connectional network. You can use this one, and then that can solve your input image size problems. So if you use SPP, no matter what kind of input image size, your output will be fixed. So after this one, SPP, you can connect to the fully connected or fully conditional layers because the output is the size is fixed. So for this example, this one, suppose we up to here, our size is W times H. Our depth, our map is 256 maps. We have a 256 maps here. Okay, so you have a recession. So we have a divided by 3 paths. So first path, this path, for each one is a maximal probability. So for this W times H map, you only have one output here. So total is 256 depth. So the only one dimension and 256 depth. So this is only one dimension, one time one dimension. Here, based on each WH, you divide it by 4 parts, so 2 by 2. Okay, and for each block, you use maximal pooling. So you have a 2 by 2 and crossover 256 depth. So the output is a 4 dimension, but the depth is 256. The same here, your output, your maximum pooling is a 4 by 4. So output was 16 and the depth. So you concatenate all together. So your output dimension will be 16 plus 4 plus 1 becomes 21. So this is total 21 unit. And the depth is 256. So no matter the input size, what the input image size is, your output will be 21. 16 plus 4 plus 1. So it's 21 dimension. Crossover 256 depth or maps. So the fixed length. Okay, that's SPP. Okay, so that's purpose for SPP. So they can solve fully connected problems. This is the other SPP. So you have your input support. Input is 512, right? 512. But you divide by actually 4 paths. 1 path, 2, 3, 4. 4 paths. But your depth is 512. And you concatenate it together. So 512 times 4 will be 2048. That's the depth. And this image size. The image size, you can do 1 by 1 convolution, so the same image size. You can do 5 by 5, this 5 by 5, 9 by 9, 13 by 13. However, your input size can do the convolution to be the same size as input. Okay. Actually, this is something wrong. Sorry, this is something wrong. This is different from this one. Difference. This is I guess the window size, the size divided by 3 is strange. Window size divided by 3. That's what I understand. What I understand is that suppose this entire is one maximum poly, like this is 2 by 2, this 3 by 3. The same as this one. 1 by 1, 2 by 2, 4 by 4. But this is 1 by 1, 2 by 2, 3 by 3. Okay, so after this one, okay, and then you do the same. This is crossover convolution and back to the original size. I say, if you do this one, it will become smaller, but you do this n by m, actually this n by m is different from this one. This one is the same as this one, crossover. So the size will be the same. And then concatenated together. Okay, there's something wrong. And then we also talk about this one. This is what I say is a deuterium. Previously we talked about deuterium. So this deuterium has from the original one, the left side, and this upsampling. So it can either add it together or concatenate together. Two way. If you add it together, the depth size, the map size is the same. If you do concatenate, the map size will be just plus together, will be longer. Okay, so that's the deuterium. Okay. And this is the same. This is YOLO V3 head. So we already talked about this one. But remember, YOLO V3, their head, the important one, they have a denominator term. So they have normalized term. So the bounding box size is not original. They need to divide it by the anchor size to be normalized. So that's good for the loss function. Okay. So last one, I'm sorry, I cannot. This is always blocked here. I don't know how to move this one. Can't move. This cannot move. Now go up. Okay. And the last page I want to explain to you is the data augmentation. This one. And in our lecture, we talk about data augmentation. About the easy one is I say it's orange. That's why your original image, right? And you do a little bigger, and you crop. That's translation. In the middle, crop one. In the top left, top right, bottom left, bottom right. So each image, you can crop it become 5 images, and then you do flip, and do the same way. You have additional 5 image. So plus 5 plus 5. So you have 10 times. So suppose originally your image has 2,000. After you do the translation and shift and cropping and flipping, and you have become 20,000 images. That's data augmentation. In here, the same. They say you crop, right? And you have a flip. So that's 2. But they also talk about you can do a little bit rotated like this one. So suppose my face is this one in the data collection. I can a little bit plus 5 or minus 5 degree rotate. Okay, and then you do the same translation, and you have more data. So this data augmentation can include rotation. So you have translation, rotation, and also can do scaling. So you can use affine transform. So that's the geometric information. For the data augmentation, you can use affine transform for your geometric information to increase more. But the other one is there's a hue, saturation, exposure. What's that? That's meaning from the RGB domain, you can transfer to hue, saturation. Exposure is the scale. Is the value. Is the bright 光线 exposure 光线. So HSV, this is V. So you can adjust this one, and then after from the original RGB, you transfer to HSV and change the lighting, change the color. Okay, and then transfer back to the RGB. So you have additional information about the color, about the lighting. So in HSV domain. Okay, so you have geometric information, you have a color domain information, and the aspect ratio is scaling. So here is about affine transform, geometric information about your color. Okay. The other one is this one. And they say you also can do is a mix up is transparent. You can use change the background and do the transparent 透明度了merge two image together and to do this one. But I never do this one before. But they say this one also can do the as a data augmentation. Remember, we do data augmentation is meaning we try to improve our performance. If your data augmentation will let you reduce your performance, that's not good. Okay, so the purpose for data augmentation is try to improve your performance of network. So let's suppose this one can improve. The other one is the original image you cut. The other one and try to do mix together. Okay, so this one my student do that. Okay, and they improve. It did improve a little bit. Okay, so let's can think about that one. Okay, so mix two this original image and cut a short patch and inside here, like a occlusion. Okay, so this improve. The other mosaic is you combine. See, suppose you do the monkey detection, but you combine some different kind of background things to here, and this become your data. Okay, and the last one is the blurring. You do blur, okay, because sometimes image is not clear, so you do blur. This is useful. So you blur your training data, input the training, and that will improve your performance. But don't do too much blurring because that will let your network confuse. Okay, so this one is very different from this geometries and color. This is just a transparent and edit the page, or this more even, more mosaic, or do the blurring. Okay, but I think blurring a little bit is okay, and rotate a little bit is good. Okay, so that's the data augmentation. Okay, so that's for the YOLO. I think I finished this one. So that's for the YOLO V4. I hope it can helpful for you. So that's the end for this semester. Okay, so after this one, if you still have a question, you can email to me, but don't write the question. We can make appointment and we can. I'm not sure whether I can solve your problem. But you can still can contact with me and we can discuss your problems. Okay, that's it for the lecture of this semester. Any questions? 有没有任何问题？就这样这学结束了啊，这是 YOLO V4 的东西啊。有问题还是可以继续问我，但我说我不一定知道哈，就是可以讨论了这样子。那如果没有的话，我们就下课，就结束这学期。那谢谢你们，谢谢你们，辛苦了。这学期比较多假这样子，好，谢谢你们，大家忙了一个学期，苦了，谢谢撑到最后。OK，那你们的问题我都有看的哈，我会继续改善自己哈，很好，谢谢你们，好，谢谢捧场，谢谢。